In this video, we're going to talk about confidence intervals, and confidence intervals are interval estimates for the population mean when the population variance is known. That is, when we use the normal distribution to estimate the population parameter. So what's a confidence interval? Well, interval estimates and confidence intervals helps us determine the accuracy of our estimate of a population parameter. To be more precise, a confidence interval, usually we just abbreviate as CI, is a 100 times 1 minus alpha confidence interval for population parameter theta. Is an interval L1 to L2 such that the probability that the population parameter falls in this interval L1 to L2 is 1 minus alpha, regardless of the value of alpha. So pictorially, what's going on is, so suppose we have a distribution, some random variable, say x. Then here's say L1, this interval is L1 and this is L2. Then the probability that the population parameter falls in, is in here somewhere, is in fact 1 minus alpha. Okay? So the area here is 1 minus alpha. And the area out here, so that the area out here is, this area here is alpha over 2. Here is also area is alpha over 2. So some common values of confidence intervals are 90%, for which alpha is 0.1, 95, for which alpha is 0.05, and alpha equal to 0.01 is 99%. So for example here, for the 90% confidence interval, alpha is 0.1 because 100 times 1 minus alpha percent is 100 times 0.9, which is 90%. Okay. So here's first confidence interval estimation when the population variance is known. Okay? So this is very important. So let's x1, x2, xn be random sample of size n, form a distribution with mean mu. So it's taken from a distribution with mean mu and variance sigma squared. Then 100 times 1 minus alpha confidence interval in mu is given by x bar plus or minus z alpha for 2 sigma over square root n, where x bar is the sample mean, sigma is the population standard deviation, n is the sample size, z alpha over 2 is the unique z such that the area from minus z alpha over 2 to z alpha over 2 is 1 minus alpha, as pictured here. So the above confidence interval works for any distribution with the population variance known. So that's for n large enough. That n is sometimes greater than equal to 30. Okay? How do we get this formula? Well, basically, you start from the definition that the probability that the normalized variable falls between minus z alpha 2 and z alpha 2 is 1 minus alpha. And then basically you manipulate this green inequality, and that green inequality is in fact equivalent to this inequality after solving and isolating for mu. So this basically says that the probability that mu falls in between these two values, which is exactly our confidence interval formula here, x bar plus minus Z alpha over 2 sigma over square root n is 1 minus alpha. Okay, so let's find out some common values of Z alpha over 2 for different confidence intervals. For a 95% confidence interval, we know that alpha is 0.05. So then here, alpha divided by 2 is 0.025. Oh, sorry, this is a typo here. And the probability that Z is greater than, okay, so this should be 0.025. So let's look for 0.025 in our standard normal table. Is there 0.025 anywhere here? Bam, right here. 0.025. So that means that is, so the Z alpha of 2 in this case is 1.96. Okay? That's why we have Z alpha of 2 is 1.96 for 95% confidence interval. What about a 99% confidence interval? So in this case, alpha is 0.01. Alpha of 2 is, sorry, this is 0.005. Then the probability that is greater than, this is going to be 0.99. So let's look for a, 0. 0.005. So let's look for a 0.005. 0.005, is there any 0.005? 0.005. So 0.005, right here almost. So it's almost here. Not quite 0.005. This is 0.005, 0508, 0.0494. So it kind of lies in between these two. Okay, so we have, so and then like that, kind of interpret. So it's like between 2.57 and 2.58. Between 2.57 and 2.58. In fact, we just chose 2.58, but we'll accept anything, any number in the interval, closed interval 2.57 and 2.58 on the final exam or midterm test. For a 95% confidence interval, alpha is 0.18. So alpha of 2, 0.05. So look for 0.05. Say 0.05 and 0.05. Around here. 0.05. It's not quite again 0.05, so we take somewhere anywhere between 1.64 and 1.65. In fact, here we just chose 1.65, which is fine. Then we can accept anything from in 1.64 to 1.65. Okay. Let's do our first example of a confidence interval estimation. So let's take a look at ergonomics, which is the study of workplaces and devices to maximize productivity and comfort. What is the preferred height of a keyboard? So this is what furniture businesses use to determine the best height for a table, right? So then what you do, companies such as IKEA or whatever want this information. So what they do is they perform an experiment. Say they take a sample of 31 trained typists, selected from anywhere. and say the after 31 typists, the sample mean of preferred height is 80 centimeters. Assuming the height has a normal distribution with population standard deviation equal to 2 centimeters, let's find a 95% confidence interval for the true average of the preferred height. So these are 95% mean confidence interval formula. Yes, because the population variance is known. So it's x bar plus or minus z alpha over 2 sigma over square root. Okay, so we have all this information. What's x bar? Well, x bar is 80 centimeters. So x bar is 80 centimeters. What's our population standard deviation? Well, it's right here. 2 centimeters. So sigma is 2. What's our size n? Well, our size n of the sample is 31, right? 31, right here. And now, what's the 31% confidence interval? I mean, 95% confidence interval. What's this Z alpha over 2? Okay, so for 95% confidence interval, we know Z alpha over 2 is just, remember, just 1.96, right? So we have everything. We have everything. So just plug it in, you get 80 plus or minus 1.96 times 2 plus square root of 31. So that means that the 95% confidence interval in preferred height of the keyboard is 80 minus 1.96 times 2 over square root 31, and 80 plus 1.96 times 2 over square root 31. This interval will in fact be 79.3 and 80.7. So the question is, okay, how do we interpret this result? What does a 95% confidence interval in this preferred height of the keyboard actually mean? Well, it means the following. Suppose, basically, you take 100 countries, okay? Say country number 1, country number 2, or up to country number 100. Let's say country number 1 is, say, USA, country number 2 is Canada, country number, I don't know, 100 is Russia. And then you take from these, each of these samples, you take 31 typists. Okay? In Canada, you take 31 Canadian typists. In Russia, you take 31 Russian typists. And so all these 31 samples, okay, yeah, you form a 95% confidence interval. Okay, so confidence interval number 1, right? You have 31 typists again, you form another 95% confidence interval. Plus number 2 confidence interval. And then all the way up to, so you form basically 100, 95% confidence interval. Okay? So what a 95% confidence interval basically means is that 95 of these confidence intervals will actually contain the population mean, and 5 of these confidence intervals will not contain the population mean. So the 95% confidence interval which is around 79.3, 80.7 centimeters. In preferred height of the keyboard means that in this example, 95 of these 95% confidence intervals formed will contain the two population mean, while 5 of these 5 of these confidence intervals forms won't contain, while 5 of these won't contain the population parameter or two population mean. Okay, so that's what the 95% confidence interval means in the preferred height of the keyboard. Let's do one more example. So suppose an operations manager of a large production plant, say, I don't know, Foxconn, those make that Apple. I want to estimate the mean amount of time a worker takes to assemble a new electronic component. Assume a standard deviation of the assembly time is 3.6 minutes. He observed 120 workers assembling similar devices, and noticed that the average time of these 120 workers was 16.2. Construct a 92% confidence interval for the mean assembly time. So again, we use here the standard deviation of the population is given. It's 3.2 minutes. Plus or minus z alpha over 2. So this is our confidence interval formula when the population standard deviation is given. Okay, so and then the population sample mean is given by 16.2, n is given by 120, and what's z alpha over 2? Oops, let's try. Well, here we're looking for a 92% confidence interval. So for 92% confidence interval, your alpha is 0.08, which means alpha of 2, 0.04. So z alpha of 2. So what's z alpha of 2 such that the error to the right is 0.04. Let's look for 0.04. So bam! Let's see what color, yellow. There's somewhere in between here and here. So let's just choose 1.75. Let's choose 1.75 or 7. It's in between 1.75 and 1.76. So I can choose 1.755. Okay. So 1.755. But remember, you can accept for anything between 1.75 or 1.76. Okay. So then you just plug everything in, you get 16.2 plus or minus 1.755, 3.6 divided by 120. So therefore your 92% confidence interval mean the assembly time is 15.6 to 16.8 minutes. And now we'll do a couple more examples of what happens when you increase the sample size, for example. So if you increase the sample size, what happens to the error? So the error in an estimate is basically this x bar. Remember the confidence interval formula is this x bar plus minus z alpha over 2 sigma over screw root in. And this is basically the error in the estimate of the. So in fact, we know that the by central limit theorem, if the size of the sample increases, of course the variance, right, decreases. So that's why the error will decrease when the sample size increases. That is, the error in the smaller sample, larger sample, is larger than, smaller than the error of the smaller sample. So let's take the example of example B1. Sorry, B1. With remember we initially started off with n equals 31 typists. Now let's change it to 50 typists. Remember the error due to the 31 typists was, let's just look back, is well 0. After 0.55, it's so 1.96 times 2 over square root of 31, which is in fact 0.7. What's the error for 51 typists? 50 typists. Well, again, z alpha over 2 sigma of square root of n is 1.96 times 2 over square root of 50, which is 0.55. And of course, we compare. 0.55 is certainly less than 0.7. So when you increase the size of the sample, your error decreases.